Good morning, everyone. My name is Mustafa. I am product manager for ProtaStructure. I have been working in Prota for more than 15 years now. Myself is also a structural engineer. I have my master's degree in structural engineering and seismic assessment of buildings. Before starting, I really would like to extend my best wishes to all who are suffering from the coronavirus all around the world. I believe that humanity will overcome this difficulty as well. So let's follow the guidance from the health people, doctors, and all the governments, and I'm sure we will be okay. And it seems that we will conduct these online events more and more often because of this outbreak and until a cure is found to this disease. So we will continue this webinar series in a more frequent manner. Any problem with my voice or the screen, please write to the questions pane. We will try to troubleshoot it. Some quick notes. Attendees are automatically muted, so you won't be able to speak. But you can use the questions pane for your queries. I will try to answer them as the time permits. But if you have your questions unanswered, please send them to globalsupport@protasoftware.com and asiasupport@protasoftware.com. Also, if you are interested in detailed information about our products, please visit protasoftware.com for detailed information. And also, there will be a short survey after the webinar. So if you can kindly fill out that survey, it would be much appreciated. I will try to get more closer to the microphone because some of the attendees are saying that the voice is unclear. Is it any better? Of course, it's depending on lots of parameters like internet connection or your sound driver. Also, I would recommend you to check your configuration as well. Okay. About today, I will talk about the seismic design capabilities in ProtaStructure. Of course, it's a very extensive topic, so it's not possible to fully demonstrate the topic in a limited time. My purpose today is to just give you an overview of the capabilities. So if from time to time I will try to open up ProtaStructure and show you some features that I'm talking about. First of all, ProtaStructure covers a wide range of international seismic codes. As you know, seismic codes are not only comprised of a load calculation, they usually span lots of topics. Of course, the starting point is the load calculation. After you calculate the seismic loads, you have to go ahead and check irregularities and perform other building checks. After that, you have to design all the members according to the ductility level you assume at the beginning, depending on the structural system. So seismic codes often override the design codes in terms of ductility and detailing, capacity design and detailing requirements. Of course, lastly, since ProtaStructure is a design software and a detailing software, as you know, it's not only a general analysis package. When you model a structure in ProtaStructure, then the final output is the design calculations and the detailing. So as a part of seismic code support, we also provide ductile and non-ductile detailing. So in summary, when we talk about a seismic code coverage, we talk about all these chapters in a typical seismic code. So what I mean by load calculation is, first of all, you have to start with a design spectrum. The seismic codes gives us some envelopes, which we call response spectra. So all these spectra are usually calculated parametrically by using the code parameters. So what we do in ProtaStructure is, depending on the seismic code you select, you can enter all the parameters in the code, and all the design spectra is calculated automatically. So let me show you in the software. For example, let me check. Okay. So when you go to the project parameters, you can select among various international seismic codes here. And if you go to seismic parameters, click on the seismic parameters. This is a parametric view, so you can use the helper tables here. You can select different site class, and at every change you make here, the spectrum is automatically calculated. So you don't have to do anything here except changing the parameters depending on your structure site or structural parameters. Here we have, of course, I will talk about this, but the ProtaStructure supports behavior factors in two directions. So you can select your structural system differently in two orthogonal systems. For example, in one direction, it can be a dual system. In another direction, it can be a moment-resisting frame system. So you will select, for example, concrete special moment frame. The behavior factor in direction 2 will be 8, and other direction 1 will be 7, and the related overstrength factors. So this is important for economical design, and really sometimes you have different structural systems in two directions, especially in steel buildings. Also, another important feature or necessity in load calculation is the site-specific spectra. So usually the code spectrum is sufficient for our load calculation. You see here the elastic spectrum and the reduced design spectrum. But sometimes in the projects you need special spectra that are specific to a particular site. So if you have such a design spectrum, you can also enter it here. All you have to do is uncheck the automatic checkbox here, and if you have a file, show the spectrum file, and then you can introduce the site-specific spectrum. We have also other options like apply accidental eccentricity. This is all applied by default. Of course, you don't have to change any setting in ProtaStructure for an economical and safe design. But if you want to experiment on these parameters, you can also go ahead and, for example, cancel the accidental eccentricity, which is 5% by default. For the concrete buildings, of course, the damping ratio is usually 5%. A number of modes to consider in response spectrum analysis and eigenvalue analysis can be input here. If the number of modes is not sufficient, the software, the ProtaStructure will give you a warning that the cumulative mass participation is not enough. given the number of modes. So this is all. There is all automation here and intelligence. So you don't miss any important steps. Also, ProtaStructure is able to check structural irregularities. Depending on the seismic code, selected seismic code, we have several of them. So most important of it is torsional irregularity. Torsional irregularity is usually affecting the analysis method to be used. As you know, there are basically two methods. One of them is equivalent static load calculation, and the other one is response spectrum analysis. So depending on the seismic region or the acceleration, spectral acceleration of the site, height of the building, and whether the irregularity exists or not, the seismic codes usually refer us to or send us to use response spectrum analysis instead of single mode equivalent static force. So all the irregularities, which are, I'm not sure if you can see clearly, but which are grayed out, the irregularities which are grayed out are checked automatically by ProtaStructure. But other irregularities such as diaphragm discontinuity, existence of re-entrant corners, or buildings with setbacks, some of them must be checked by engineer by visual inspection and checked here to include it in the reports. But if you have diaphragm, for example, if you have diaphragm discontinuity, by the way, I see some questions on the question pane regarding the sounds. I believe the sound is okay because majority of the attendees is not complaining. So regarding diaphragm discontinuity, of course, we do not, ProtaStructure does not decide whether the diaphragm discontinuity exists or not. But if you I will talk about it. You can use flexible diaphragms, or you can exclude any slab from rigid diaphragm formation to facilitate the diaphragm discontinuity calculations. Anyway, so let's continue. The first important step in seismic analysis is the mass calculation. Of course, in a structure, the masses can be calculated from different sources. In ProtaStructure, when you insert slabs, beams, or slab loads, or other loads you can think of, all the loads are automatically decomposed onto the beams. Okay, you don't have to define every loads from scratch, every load, frame load, or point load from scratch, like in a general analysis package. So all the loads are automatically derived from the self-weight of the structure, obviously. You may have imposed loads or user-defined loads, slab loads like point, line, area, and wall loads on the beams. So all these masses are automatically derived and converted to seismic mass, which is a combination of self-weight plus a portion of the imposed loads. And what is that portion? It is the live load participation in seismic codes. In ProtaStructure, we support different live load participation for different stories. So it's very frequent that first 3 or 5 stories of the building, we say podium, for example, can be used as a shopping mall, with a higher load participation, and the higher stories can be office areas or residential areas. So it may have a lower participation ratio. So you can control this participation factors for each and every story you have in the structure. Let me show you a little bit about this. Let's cancel it. So what I'm talking about while saying the mass. So here you see the slabs defined, inserted between the beam regions. The first method of load decomposition is the yield line decomposition. So by default, all the slab loads are decomposed onto beams by yield lines. So if you investigate one of these, sorry about this, okay, yeah. But if you use the yield line decomposition, you'll see that we have triangular and trapezoidal loads on the beam automatically transferred from the slabs. So we also have the self-weight of the beam, and the ProtaStructure will calculate the mass automatically from this load profile. So you don't need to touch anything. The other method of load decomposition is finite elements method. You can isolate a single story of the structure and decompose the loads of slabs by finite element decomposition. Since I have not done any decomposition, finite element decomposition here, you don't see any slab loads yet. But the default method is the yield line decomposition. So and you may have line load, point loads, for example, 2 tons of point loads here, for example. A line load or a patch load, maybe spanning two slabs at once. So all these extra loads are also converted to mass and considered in the seismic analysis. Besides, you may have some, let's see, you may have an infill partition wall on the beam. Okay. This also creates, let's investigate the member loads. So now we have a wall load here, extra wall load here. So all these loads are considered in the mass calculation. Also, you can create new loads on the beam, which we call user-defined loads. So using one of the profiles here, you can create a custom profile. You can enter the dead load and the live load values of this profile. And these are also considered in mass calculation. Other important topic is the diaphragm modeling and Storey meshing. ProtaStructure provides very extensive, actually, options for this. The first obvious option is the rigid diaphragm assumption. You can use a single diaphragm or a multiple diaphragms on a floor. The powerful feature of this is ProtaStructure can automatically decide on number of diaphragms on a single floor. ProtaStructure will check the connectivity of the slab members, whether they are touching each other or stepping aside from each other. It can decide on the number of diaphragms on the floor. You can assume a no rigid diaphragm approach. Okay, even if you have slabs on the floor, you can assume that the building has no rigid diaphragm. That's also possible. ProtaStructure also supports flexible diaphragms. You can mesh stories selectively, and you can use finite element decomposition, and you can include columns outlines in the analysis. So what I mean is, so let's go to building analysis. In the model options, I'm not talking about Shearwall model yet. In the slab model, we have 3 options. One of them is the rigid diaphragm, slabs to define rigid diaphragm. This option will allow ProtaStructure to decide diaphragms itself. So there's an intelligence behind it. As I said, looking at the slab connectivities, the diaphragms, rigid diaphragms will be created automatically. You can force the system to behave as a rigid diaphragm for each floor, or you can assume there is no rigid diaphragm in floor levels. These diaphragm models should be considered in conjunction with the finite element mesh, because if you include the slabs in building model, you can also select which slabs, which floor levels to be meshed. Usually in seismic codes, you don't need to mesh each and every story because a frame approach with distributed loads of the frames is usually an acceptable approach in design. But if you have a flat slab, of course, you must mesh all the stories, all the floor levels. But if you have a beam plate structure, a frame structure, usually it may be sufficient to mesh only the transfer floors, or the floors, the basement floors, or the floors where the structure transitions from a podium to a tower. So ProtaStructure will allow you the flexibility to mesh the slabs by floor level. So here in this example, for example, since I have basements in the structure, one basement, so I only mesh the first basement ceiling. So now, since I included slabs in the building model now, and I select the no rigid diaphragm approach, it will be a flexible diaphragm for the first story. But the better option would be I will allow ProtaStructure to define a rigid diaphragm itself, but I will assume rigid diaphragms for stories 2 to 7, but I will uncheck the first story by saying that, okay, use rigid diaphragm for these stories, but do not use a diaphragm assumption for the first story. And since I include the first story mesh in the analysis, that means first story will be, or the basement ceiling will be a flexible diaphragm, whereas the other stories will be rigid diaphragms. So this is all very flexible here. You can control the shell size here. It will affect the analysis time considerably. Usually you don't need to do very fine mesh, but very coarse mesh is also not good for vertical load distribution. We are aware of this fact because meshing the floors for lateral stiffness and meshing the floor for vertical load distribution are different things. So for usually the approach is the engineers tend to mesh the floors very coarsely, because meshing all the floors is really in a fine manner really takes a lot of analysis time. But since they also tend to use the same coarse mesh for the vertical load decomposition, all of a sudden the gravity loads on the beams start to be inaccurate. In ProtaStructure, we have several options for that. For example, if you check use decomposed slab loads here, that means you want to include the slab loads. You want to get the slab loads from the finite element mesh. In that case, I would not recommend a very coarse mesh. But if you uncheck this, that means you will mesh the slabs for lateral stiffness, lateral behavior, but you don't want to use the load decomposition from the finite element mesh. You still want to use the load decomposition from the yield lines or other options. If you have large columns like 80 by 80 or 1 meter by 1 meter, and if you think that the column sections will affect the mesh considerably, You can include the column sections in the finite element model. Usually, this will bring a more accurate and more economical design, because modeling columns as a single point in the finite element mesh is usually causing some peak moments in the design, which are not realistic and which will yield uneconomical design. So you can include the column sections in finite element model to overcome this difficulty. So this is also possible here. And the other important thing is you can control the slab stiffness coefficients in a very detailed manner. So you can control the in-plane membrane behavior of the flexible diaphragm, or you can control the bending behavior of the slabs. So usually I would recommend reducing this to like 0.25 or 0.35, because under the gravity loads and under the long-term effects, the slabs will crack, and we don't want in our beam design, we don't want the slabs to be effective. So we usually reduce the out-of-plane stiffness for the slabs, and also depending on the assumptions you make, you can also reduce the in-plane stiffness of the slabs as well. So I will not touch it here. So let's continue. Sorry. With the shear wall modeling, ProtaStructure supports mid-pier and shell modeling options. Both these models have their own merits. For example, mid-pier is a frame approach in which you model the frame, you model the shear wall with a central frame with rigid arms. It will bring speed, and it will bring speed to analysis, and it will be effective. But shell modeling is, of course, considered as the state-of-the-art modeling option for shear walls. Also, we support core wall modeling. And we have a special wall type called basement wall. The basement walls are always modeled as shell. And also you can use different crack section properties for walls. In seismic codes, usually the different crack section properties are used for different members. Let me talk about it here. Okay, so mid-pier model, you can. This is the default modeling throughout the structure. So if you select mid-pier model, all of the walls will be mid-pier, modeled with mid-pier. If you select finite element, it will be the default modeling for all the walls in the structure. So you can control the mesh sensitivity as well here. Okay. If you have core wall panels, you can control the modeling of core walls as well. Usually what we do is we still model the core walls with at different panels, mid-pier or shell model. But in some occasions, you may need to model the core walls with a single mid-pier. So this is also an available option. Besides, you can also select the wall and change the wall model from default to mid-pier, shell, basement, or retrofit wall for a particular wall member. So it will not be using the default model anymore, but it will use the one you selected. In this example, let me check the. Okay, if you look at the building in the 3D, you can see that some of the walls are blue and some of them are green. That's because we have set these walls as basement wall. Basement walls are always meshed because they are effective under shear more than bending. So because of their aspect ratio, it's better to model these walls as with finite element shell members. But if the aspect ratio of the wall is more than 2, I mean the entire height over the length is more than 2, you can model them as mid-pair elements. So it will not change the results too much. But also in ProtaStructure, we have these core wall members. You may select several panels and merge them into a single core wall. Of course, these core walls will have some torsional behavior. It will not be a good idea to model this with mid-pair members, because you may not be able to capture the desired behavior with mid-pair elements, depending on the wall size and wall complexity. Because mostly these core walls are open sections, and open sections are very weak in torsion, as you know. So the warping and the torsional effects can be captured by shell elements more effectively. There's another wall type, of course, which I will not talk about too much, is the retrofit wall. If you are doing assessment or a retrofitting in ProtaStructure, what you usually do is you install in place reinforced concrete frames, shear walls between the existing columns and the beams. So you can also denote a wall panel as a retrofit wall. In this case, of course, we will calculate the dowels and the other longitudinal bars accordingly. So you can also use the retrofit walls here. Anyway, so let me do the analysis here, if you like. So let me check the parameters quickly. Okay, seismic parameters. Okay, and model options. I will use the finite element shell model. Okay, I will go with these options here. Okay, let's do the analysis. I'm reading the questions, by the way. So yes, the question is, does it mean that we can analyze multiple towers in the same model? Yes, you can analyze the multiple towers because when you separate the floor plans, which are not touching each other, so ProtaStructure will automatically detect that these are separate diaphragms from each other. So you can analyze the multiple towers in the same model. So another question is, no rigid diaphragm floor means flexible or semi-rigid? It depends on the model you select. If you mesh the slab and select no rigid diaphragm, it will be a flexible diaphragm. But if you don't mesh the slab, then it will be a no rigid diaphragm option. For crack section properties, can we define a specific member, or is general to all sections? It's both. You can define the general crack section properties, or you can set it for a member as well. Anyway, so what we did here is we completed the analysis. Okay. In ProtaStructure, since you are dealing with a physical model, it will convert the physical model automatically into an analytical model, of course, and it will analyze the building under the given assumptions. So after this, if you pay attention here, the building analysis is completed. So now post-analysis processes began. So we calculate this, we check the irregularities, we check the second-order effects, and all the lateral drift checks are done, and the design information is extracted and made ready for the design and detailing, and it's completed successfully. So let's check the analysis results. Okay, so you can see the mode shapes of the building here. If I exaggerate it's a little bit more. So I think because of the distribution of the shear walls here, the first mode of the building is a torsional mode, which is not very desirable. But the X and Y translational modes are the second modes and the third modes. Still, they are not ideal because the structural displacement, the modal displacement, also includes a coupling in X and Y. So it's not a pure X or pure Y translation that we observe. So usually you can fine-tune your structural system by checking these mode shapes and whether there are coupling in different directions in displacement shape. I will talk about very interesting things here, but okay, let's check the equivalent static for the upper part of the structure. So it's better, I think, for the Y direction. Since I have a basement in this structure, ProtaStructure performed a two-stage analysis in which we have a superstructure analysis first with the basement mass of the basement 0, and we have a basement analysis. Let me exaggerate it. As you see, the upper structure is acting like a rigid body, and only the basement floor is deforming. So the second stage analysis is the loads applied only to basement, and the upper structure loads are non-existent, lateral loads are non-existent. So ProtaStructure combines these two analyses for the basements with the buildings with basements, because as the seismic codes recommend, in the vertical direction along the height of the building, especially basement stories have very different stiffness characteristics than the upper stories. So seismic codes prefer to or suggest to analyze basement stories, basement levels separately from upper stories, or they recommend a two-stage approach, two-stage analysis approach, in which one of the analysis you set the basement masses as 0, and you do eigenvalue and equivalent static analysis or Mode-Superposition. Then you set the upper story masses as 0, and you analyze only the building, and you combine the results with the redundancy factors or with different overstrength factors. So this is the approach usually in seismic codes, and ProtaStructure adapts it for the basement, the structures with basement. Anyway, so let's check the model a little bit. So as I requested from ProtaStructure, the basement floor is meshed, compatible with the other walls. The basement walls are also meshed, and the other walls are also meshed here, since I wanted to use the finite element model here. So you see the core walls here as well, which are also meshed with the shell elements. So let's check. Let's check the moment diagrams for Let's continue with the presentation and try to stick with the flow. Okay. Another important modeling is the wall coupling beams. Usually, the walls with coupling beams or without coupling beams have different ductility properties, ductility features. And depending on whether they exist in the structure or not, the selected ductility behavior factor may change. And also these coupling beams require additional detailing, special detailing. And also they have effects on the wall assembly behavior. So seismic codes usually require to check this coupling beam effectiveness. Even coupling beams will get a different crack section properties in the analysis. I talk about crack section properties a lot, so let me show it to you. In the model options, we have an effective section stiffness factor table. So as you see here, if you are using shear walls with shell members, different crack section properties can be used for each and every degree of freedom or the property. If the shear walls are modeled with frame, you can set different crack section properties. Basement walls, likewise. Slabs, similarly. So you can control the groups of members very in a detailed manner to use this crack section properties. So if you see at the bottom, we have coupling beams. So coupling beams have also can have different crack section properties depending on needs. So these are granulated in ProtaStructure, and you can control them as you wish here. And talking about load cases and combinations, okay, so we have a loading generator. You can define any vertical loads or pattern loads here. I'm not going into detail of it, but for horizontal load combinations, you can use equivalent static loads or model response spectrum type load cases. We have several options like include the 0.9 G plus E, which can be critical when the axial load due to vertical loads are lower. So it can be these combinations can be critical. Also, seismic codes also require application of the 30% of other direction to the major direction. So this also can be considered here. And lastly, we have an earthquake. You can apply the earthquake loads in the structure. It's usually a percentage of the G or self weight. So depending on the design spectral acceleration in a short period, which is SDS. So these all can be applied in the structure. So if you hit OK, all you have to do is click OK. So the combination set is automatically created. So it will include that plus live, which is patterns and non-patterns. Also, we have crack section. This is important actually. I have to talk about it. So D means uncracked, DC means cracked. So L means uncracked, LC means cracked. So in ProtaStructure, you can use cracked and uncracked stiffness matrices in the same combination, because seismic codes usually require us to use uncracked properties for example, dead loads, or different crack section properties for dead loads when they are combined with earthquake. And if they are not combined with earthquake, they will use different crack section properties. So you can use it here. As you see, the uncracked D is combined with a live load only. but correct dead loads is combined with live loads, correct live loads, and vertical earthquake and the spectral load case. Sorry. If you take a look at the load cases, these are also automatically created. So let's double click and check one of them. So it's a lateral load with equivalent static feature, and it's a load case in primary direction with a eccentricity in secondary direction. So all these accidental eccentricities are automatically included in the combinations. Another important thing is, for example, you see the 8th load case is EX plus, which means that this load case is acting in X direction and rotating the floor plan in a clockwise direction. And the 10th load case is EX minus, which means still it's acting in X direction, positive X direction, but it's rotating the floor plan in counterclockwise direction. These can create different critical effects in the design. So these are also automatically taken into consideration by ProtaStructure. So at the end of the day, if you look at the combinations, for example, D plus self dead load, live load plus EX plus, dead load, live load minus EX plus, all these load cases are combined so that the symmetrical and the critical values are attained for the design. So this is a really important topic. Even with a operation as simple as load combination, there are lots of details when you start talking about seismic design. Okay. So I think I mentioned about the eigenvalue analysis. So the eigenvalue analysis is done automatically, including the torsional modes and inertial masses. And the ProtaStructure determines the dominant mode automatically from the mass participation. And also we utilize the correct sections in eigenvalue analysis. So equivalent static load method is also inside the software. So these loads are automatically calculated and distributed at Storey levels. As I mentioned, we may have multiple diaphragms or free nodes. If this is the case, the Storey shear is distributed among them. So if a floor has multiple diaphragm as well as a free nodes, a mixture of them, the total Storey shear is shared among them. Also, as I said, accidental eccentricity is automatically calculated and applied, and also irregularity penalties are automatically applied. So what is the irregularity penalty? For example, if you have a torsional irregularity, the penalty of this torsional irregularity is increase the accidental eccentricity. So if it is 5%, the penalty is to increase it to 6%, for example. In that case, the ProtaStructure will repeat the analysis automatically again with the increased eccentricities and give you the results. So usually, since equivalent static method is an approximate method, and it's dependent on the first mode, it will have penalties if there are irregularities in the building. Also, regarding the Mode-Superposition method, you can use the mode RSA analysis, response spectrum analysis, where the equivalent static laws are not applicable. We combine the model results with CQC. Also, we apply the accidental eccentricities automatically again. The important thing is Mode-Superposition method is the comparison of results to equivalent static. So seismic codes do not allow to use the Mode-Superposition alone. You have to upscale the results from RSA to equivalent static. So this is also done automatically for all the drifts and all the internal forces. And also another important check for mode superposition is the mode participation. Depending on the seismic code selected, the cumulative mass participation should exceed 90%, 95%, or even 100% in some cases. But of course, attaining a 100% participation is not, of course, attainable using the limited number of modes. So the mode participation is also checked automatically. Here in the screen, you see some screenshots from the software. Okay. This slide is about the analysis method. If the selected analysis method is not applicable for your building, ProtaStructure will warn you. It may depend on different parameters like seismic design category or risk category, stories above base, height of the structure, whether irregularities exist or not, whether the period of the structure exceeds some limit or not. So all these analysis method checks are done automatically in ProtaStructure. If your selected method is not applicable, the ProtaStructure will warn you about it. I also talked about behavior factor. You can use different behavior factors in two orthogonal directions. I will not talk about it in detail since I already showed it to you. I talked about the stiffness modifier table. As I said, you can control the crack section properties very extensively using this modifier table. And also the important highlights here is the ability to use the different stiffness matrices for different load cases. So for uncracked sections for gravity combinations and cracked sections for earthquake combinations. These are all possible. I talked about two-stage analysis. If you have a basement structure, the two-stage analysis is automatically done by the ProtaStructure. I also talked about vertical earthquake effects. We can pass this quickly. Another important check is the building base and building height check. So let's switch back to ProtaStructure here. When you start the modeling in ProtaStructure, you usually go to Edit Story dialog. Okay, so you say that I have one rigid basement here. Number of rigid basements is 1 in this example, and the effective top story is 6. Since I have some elevator floors here, I don't want to consider them in irregularity checks, and I don't want to apply the top roof load to these stories, but they are still in the analysis model. They are not excluded. Their stiffness and mass contribution is not excluded, but they are excluded from the irregularity checks and the in equivalent static load method, the roof load is not applied to this story level. So anyway, so when you design when you start the design, you usually start by setting the story properties. So in this example, I have one rigid basement, but according to seismic codes, it's not sufficient to say that I have one basement. You have to satisfy certain criteria, which is, for example, the period of the entire building with basements over the period of the first period of the upper stories only should satisfy some certain ratios. So if the criteria is not met, then that means you cannot assume that you have a rigid basement. Or in order to assume a rigid basement in your structure, really you must have rigid walls around the basement level. So if you don't have any walls, you cannot say that I have a rigid basement. Or if the periods are not satisfying the given code criteria, you cannot say that I have a basement. So ProtaStructure decides whether the building base or the basement number is acceptable or not. This is a very important check, which is usually overlooked by engineers and other software. What we check, actually, I mentioned about these irregularities at the beginning of the presentation. We check floor torsion. The penalty for the floor torsion is amplification of the eccentricity, additional eccentricity, and repetition of the analysis automatically. So you don't have to do any analysis by yourself. The ProtaStructure will take care of it. Another irregularity is extreme floor torsion. Again, the eccentricity is amplified. These two also affect the selection of analysis method. You may have diaphragm discontinuity. You can handle diaphragm discontinuity by using flexible diaphragms, multiple diaphragms, and free nodes. You have these modeling tools at your disposal to consider diaphragm discontinuity. Also, if you have non-parallel systems, non-orthogonal systems, the penalty for it is usually the addition of 30% of other direction to the major direction. So this is also achieved automatically by ProtaStructure. Regarding the vertical irregularities, ProtaStructure checks soft story, extreme soft story, or mass irregularities, vertical geometric irregularities, weak story, or extreme weak story. These are also important, and also these affect analysis method selection. These are all in the software. You can go to the post-analysis reports and take a look at the tables, which are also included here as screenshots. A relative story drift check is very, very important, because even you satisfy the strength and ductility criteria in your building, story drifts can be exceeding the allowable limits in the code. So these are also checked against the code regulations and tabulated for you. So this is a very important check as well, which must be done. A second order requirement check is another check, and it's an indicator of potential influence of second order effects. It's basically the moment created by the lateral loads, earthquake loads, over the moment created by the moment created by the vertical loads, dead loads, over the moment created by the lateral loads. So if there is a significant moment created by dead loads due to lateral deformation, then it will be an indicator for us that the structure would suffer second order failures or second order effects. So design will be dominated by these. A simple stability check is a seismic overturning check. It compares the overturning moments versus resisting moments. This is particularly useful for narrow buildings, or if you are designing towers, you may take a look at this overturning check. Of course, it has to satisfy some certain safety factors. Very important check is the strong column and weak beam check. If you are doing a special frame design, okay, you have to check you have to satisfy the strong column, weak beam philosophy. What we do, we calculate the capacities of the columns, and we calculate the capacities of the beams, and when you divide them to each other, you get an indicator which should not exceed some certain value depending on the code. So this is an important check which should be done. Also, joint shear check is done automatically. For the strong column check, usually it's sufficient to satisfy the 70% of columns in one story. You don't have to satisfy the strong column rule for each and every column at a story level. The 70% is usually sufficient. But for joint shear check, since this is a check that prevents the brittle failure of joints, each and every joint must be satisfying this shear strength condition in this case. And also joints are automatically classified as type 1 or type 2 joints, which are confined joints or unconfined joints. If there are 4 beams framing into the column at 4 sides, and their perimeters are more than 75% of the perimeter of the column, then it is a type 1 joint. If it is an exterior joint, then it's a type 2 joint. So this check is done automatically. So after these structural checks, we go into ductile checks like ductile beam design. So what we do is we first of all, including all the seismic combinations, we create the envelope diagram, including the gravity combinations and seismic combinations. We have the envelope diagram, and depending on this envelope diagram, we calculate the longitudinal bars. And of course, all the seismic code provisions are applied on the amount of longitudinal required area. But shear design is another very important thing in the seismic codes. So we don't design according to the shear diagram we have at the end of the analysis. We have to go for the capacity shear especially for the high ductile beams. So what we do, we calculate the capacity shear, which is the ultimate shear that will affect if the both ends of the beam is yielded. So we calculate this capacity shear using the formula given in the seismic code, and we calculate the amount of links using these capacity shear values. Ductile column design is similar. So also for ductile design, we have to make sure that the column does not fail under shear forces. So the capacity shear approach is also utilized here. Also, the axial loads are limited in seismic codes. So, for example, you cannot exceed the 40% or 50% of the section capacity in the seismic design. You have to create confinement zones. That's another necessity. But one important thing is the automatic containment. In order to have an effectively confined concrete core in the column, we must provide sufficient amount of links and tie bars to confine the concrete core. So you can select to use a single link for the columns and try to satisfy the containment with tie bars, which is the first option. And in the second option, you may choose to use double links and the tie bars where necessary, triple links plus tie bars, or diamond links. So depending on the column size, okay, you can tell. Let's make it bigger. Okay, you can tell ProtaStructure if the aspect ratio of column is less than 1.8, use these options. If the aspect ratio of column is greater than 1.8, use other options. So in order to provide effective containment, then you can select these options. By the way, all the tie bar spacing and all the link spacing is calculated automatically for satisfying the containment. I will show it with the next slide. So, so for ductile column design and detailing, one option is to create the lap splices in the middle region of the concrete. Okay, there are two options in ProtaStructure. You can You can create the lap supply. You can splice the longitudinal bars at the Storey level, or you can splice the bars in the mid region. Depends on your choice of practice and the seismic code requirements. Also, you may have a narrowing column. If you look at the section of the column, in the upper stories, the column may be narrowing down. So there are some certain criteria that should be met when the longitudinal bar from bottom story is going into the upper column. So this inclination here must satisfy some certain conditions. Usually the inclination is 1 to 6. So if the 1 to 6 option, 1 to 6 criteria is not satisfied, the longitudinal bar is simply left as it is or bobbed into the beam. You may have inclined sloping columns, and again, these are also detailed. As you see here, more closely, let's make it bigger. Okay. Here, this bar is automatically going into the upper column, and the lap splices are in the middle. But this bar here is not satisfying the inclination ratio. It's left as it is. Another important topic in design is the ductile wall design. So first of all, shear walls must also satisfy the capacity shear design. So we don't usually use the analysis shears again. We calculate the capacity shear forces. Another important thing in wall design is the design of end zones. So this is done automatically in ProtaStructure. Usually the idea is to from a certain distance from the bottom to top, some of the stories, usually it is the height 6 times the length of the wall, or the total height divided by 6. Some certain criteria, there are some certain criteria for critical wall height. If the wall is in that critical wall height, then the end zones are larger. That's determined automatically by ProtaStructure. And if the wall is outside a critical region, then as you see here, the end zones will be narrower. Also, if the shear wall is narrowing down more than 20% of the length, so also critical height should start over again, and larger end zones must be used in that case. Again, all these details are done automatically in ProtaStructure. Another important concept is the moment envelope for the shear walls. So again, for the moment flexural design, we don't use the analysis moments for the shear walls. What we have to do is we have to assume as a constant moment within the critical height, and we draw an envelope to the top and use that envelope in the moment design. So that's an important thing to consider. Also, we support different detailing options for shear walls. As you see here, the shear wall section, we support options for the web bar to go into the end zone, inside the end zone, and make a bob here. We also have options to web bar to continue outside the end zone or inside the end zone. So these are all different options for wall detailing that are already inside the software. Some of these details might be preferred because of effective confinement. Another topic is the seismic isolators. So you can model seismic isolators in ProtaStructure. Currently, they are linear elastic springs, and we perform linear elastic analysis with the isolators. So what you have to do is you can after you do the initial isolator design, you decide on the stiffness of the isolators, or how to say second stiffness, or the effective equivalent stiffness of the isolators. You can introduce them to ProtaStructure to perform the design of upper structure with under elastic loads. So this is also possible in ProtaStructure. You can choose among lead rubber bearing, friction pendulum. Sorry. And you can insert these isolators in anywhere on the building. For example, one of the projects we did with ProtaStructure, some of the isolators were at the bottom of the building for isolating the elevator shafts and the stair shafts, but other isolators were at the top of the basement because we had some car park facilities. So we had to isolate different levels of the building. So let's talk about assessment and retrofit a little bit. ProtaStructure supports different methods for assessment of existing buildings. So one of them is displacement-based linear elastic methods, single mode static pushover, risk assessment, and nonlinear time history analysis. So among these, the risk assessment is a special analysis. It's again a displacement-based linear method, but the performance level of the risk assessment is between life safety and collapse prevention. So it provides a quick way of deciding whether the building is really risky or not. So after this risk assessment, the demolition or retrofit decision will be made. So also in ProtaStructure, we support some retrofit techniques like column jacketing, in-frame RC walls, and steel braces. There are some powerful features here. So when you assess the buildings, what you usually do is you go into the building physically and you take measurements. You create you just have an understanding of the existing state of the building by taking measurements, by taking samples from the concrete, by breaking out some concrete covers and look at the existing bars, corrosion levels, etc. So first of all, you have to collect information from the buildings first. So that means if you have the blueprints for the building, you may have the exact reinforcements in the project, or you will have the estimated reinforcements. So that means when you if you have the blueprints, you can enter the rebars one by one to the columns in ProtaStructure, and then when you go to the existing building on the site, you may realize that actually the rebars in the blueprints are not matching with the existing state. So you can just use the rebar realization factor. So for example, you have some rebars on the blueprint, but 80% of it is used in the project, in the application, or the building may be suffering from corrosion. So you can also enter the amount of corrosion in the building in ProtaStructure. So depending on the information you collect from the building, you have an information level for the building. So it may be a limited information, a detailed information, or you may have another level that you seem appropriate. So all these information levels will yield to a capacity factor. If you have a detailed detailed information, collected detailed information from building, then the capacity factor will be 1. If you have a limited information, the capacity factor, for example, will be 90%. And after before starting the assessment, you will need to state the performance targets. So usually what we have is the different earthquake levels. It may be MCE level earthquake with the return period of 2,475 years, or it may be a design earthquake, DB earthquake, with a return period of 475 years. So under these different earthquake levels, you must set some performance level criteria. So you may say that, okay, under the DB, I want controlled damage, and under MC, I also want controlled damage. And for lower earthquake levels, like 72 years or 43 years, I want limited damage performance criteria. So of course, depending on the client's needs, there are two factors on this. The seismic code may be specifying these performance levels, or your client may be specifying these performance levels, depending on the investment they made on the building. So actually, what I'm trying to say here is you can use this assessment menu, assessment dialog, not only for assessment, also for performance-based design. So when we talk about assessment, we must talk about the ProtaStructure and OpenSees integration. This is introduced in the last service packs of the version 2019. As you know, OpenSees is the open system for earthquake engineering simulation. What we support is we transfer the entire analysis model to OpenSees by TCL files. All the nonlinearity definitions are automatically calculated and assigned. And also we can perform a nonlinear pushover and time history analysis. One important thing is the result post-processing. When you do a pushover analysis and time history analysis, usually there are lots of data to be post-processed. So this is also done automatically. What we do here is for calculation of material nonlinearity, we use nonlinear fiber analysis for sections. We discretize the section using the fibers, and we use the stiffness-based nonlinear approach for calculating moment curvature analysis for moment curvature curves and interaction diagrams. And also we use the distributed plasticity approach for the frame members, which is the finite length hinge zone. So we assume plasticity distributed along the plastic hinge length. For pushover analysis, what you can specify is the monitored node. You may be doing this pushover analysis for the entire structure and monitor the top nodes, or you may be performing a Storey pushover, and you may want to monitor a node at a Storey, which is usually the diaphragm master joints for the top Storey or any Storey you like. You can control the target displacement and iteration parameters in a very detailed manner. So at the end of the analysis, we have a pushover curve and a detailed assessment report. What we usually do in the assessment report is to calculate plastic rotations, and yield rotations are also known. So we compare these rotations with the rotation limits given in the code. That's the typical approach. So for the nonlinear time history analysis, first of all, the most important thing is the selection of the accelerogram, the ground motions. You have to select, depending on the building site, you have to select the appropriate ground motions which which is similar to the faults near to the building site in terms of fault mechanism, etc. So you have to select this appropriately. You cannot just select a random ground motion and do the nonlinear time history analysis. The fault mechanisms and magnitudes must match in terms of with your building site. Also, you cannot use a single ground motion for the time history analysis. You have to use at least 7. Of course, these criteria is different from seismic code for each seismic code. So if you use, at least you have to use 3 ground motions. Okay, if you are using 3 ground motions, you have to use the maximum response envelope. If you use 7 ground motions, you have to use the average response. Some earthquake codes, a few earthquake codes require you to use 11 ground motions and use the average of this. So, but usage of 11 or 7 ground motions is not enough, because you have to apply these ground motions in positive X or negative X directions as well. Depending on the floor plan, they may create different critical effects. Also, you have to select ground motions for X and Y directions and apply them simultaneously. So there are lots of details in selecting these appropriate ground motions. Also, these ground motions selected must be scaled according to a given code spectrum. So you cannot just use the ground motion as you download it from peer database. So you have to look at your code spectrum and between given period levels, which is usually the dominant periods and dominant period over 5. Between these 2 levels, you have to scale your ground motions to match at least 90% at least of the target spectrum. So there's a scaling. ProtaStructure automatically scales this for you. Also, another important thing is the post-processing. Consider you selected 11 ground motions and you did the time history analysis for these 11 ground motions. Considering positive X and negative X, you have 22 separate analyses. And from this 22 analysis, you have thousands of data that you have at the end of the analysis. You have to post-process this to get the average response. Average of maximum responses, to be exact. So for each ground motion, you have maximum response, maximum positive or maximum negative responses. And for each of these ground motions, you have to calculate the average of these responses for 22 analysis. So there's a huge amount of post-processing that needs to be done. And this is also done automatically by ProtaStructure. And after this, the assessment report is also created similar to Pushover, because what we do is a nonlinear time history, and what nonlinear time history gives us is the plastic rotations, again, similar to Pushover. Then we create the assessment report at the end of this analysis. So I'm exhausted. So as you appreciate, this is a very detailed topic, and we can talk about this hours and hours, and still we can have lots of questions and lots of things to remember and lots of things to talk about. But what I wanted to do today is to summarize the seismic capabilities of ProtaStructure in like 1 hour and 1.5 hours. I tried to show some important concepts using the software itself, and I prefer to talk about it using the slides. I hope it was beneficial for you. I hope you enjoyed the presentation. If you have any questions, please drop them to the email addresses I gave at the beginning. Let's just roll back to the slide here. So if you have questions, please send to these email addresses. We will be glad to answer them. I hope you enjoyed it.